Okay, so plugging this whole thing in for radius, making sure to keep 2/5 within these parentheses because we're going to square the whole thing. And so, as a property of the exponent, you can square each of these individually, this term and this term. And so we've got the 4/25. Please don't make the mistake of distributing the exponent to this sum of two values. And I always say sum because when you subtract, you're adding a negative. Anyway, you do not get 10 squared minus xi squared, or plus, quote, negative xi squared. So, don't do that. Now, we get this here, and I'll show you a little trick for calculating this by hand. If you're dividing something by 25, divide it by 100 and then multiply it by 4, and you can often get the result in your head. Alright, so you want to divide something by 25. It's as if you're dividing by 100 and then multiplying by 4, because 100 is 4 times as much as 25. Easy to divide by 100, especially when you have these two zeros. I'm just going to say all of this. By 100, you have 98. Multiplied by 4, you have 392. Now that part you can do by saying 98 by 4 is 100 minus 2 by 4. 100 minus 2 is 98. So 100 minus 2 times 4 is 400 minus 8. 400 minus 8 is 392. So we've got 392 pi right here. Alright, so I added these steps. I like to do these little side things. You can continue on in this video if you want to see the answer now. It's pretty straightforward. But anyway, we divided 9800 by 100 and 98, but we multiply by 4, and this is very close to 100, so you've got this 400 minus 8, 392. Well, we want to multiply 392 itself by 4. 392 is close to 400. It's 400 minus 8. So, distributive property again. 1600 minus 32. Well, let's subtract the 30 first. That's 5700. Wow. No, that's 1570. And then subtract 2, that's 1568. And so we've got 1568 pi, and let's just get this done with. That's 10 minus, let's just focus on the xi now. Xi squared. I guess I'll keep this in green. Delta x. So remember that this is the force required to move the ith disk all the way up to the top of the tank. And so let's just get rid of this real quick. Now, what about work? Remember, we finally want to deal with work. And we did all of this for the express purpose of representing this in terms of knowing that I'm going to, at any given point in this thing, if I have a stack of disks, I'm going to take those disks and move them a distance that we've determined to be xi based on similar cones. And so we found the radius of the disk, which is the most important because the radius is changing as we're moving from top down to bottom, radius or radii of each disk. And like I said, we want to calculate force in terms of, alright, the distance from the top down to the disk. We're eventually going to move that disk. And so that's what we did. And now we have this in terms of this very, very important piece of information. So now let's express this in terms of the amount of work it would take to actually first apply the force to overcome what would be the acceleration of gravity. I didn't write the gravity constant, of course I multiplied by it. So the force is overcoming gravity, applying that force, and then moving at, this is overly simplified, but moving at some kind of constant rate upward. We're just applying force over a distance. And so we have work on the ith disk is equal to force on the ith disk multiplied by that distance that the ith disk is moved.